All right, so for the second portion, technically, is lipid biosynthesis. So now we're going to start talking. We did the simple ones up to 16 carbons for a saturated fat. We haven't desaturated it yet, make a polyunsaturated or an unsaturated fat. We also haven't, we need things that are really big, arachidonic acid and things like that. So how do we make those? And that's what this is going to build off of. First of all, palmitate or palmitoyl-CoA, because that just means it's still attached to coenzyme, or it is attached to coenzyme A. It's the building block. And as I just mentioned just within a few minutes ago, last few minutes, the elongation beyond that is going to occur primarily in the smooth ER. There is some that occurs inside the mitochondria. Then one of the problems we have is if we want to make an unsaturated fat, is how to desaturate it. How to put in those double bonds. It's not like organic chemistry, we don't have certain the same conditions. We just can't do free radical halogenation all of a sudden to make it a better amine or what have you. This also occurs in the ER. And for whatever reason, B mammals can only put in double bonds as far as C9 and 10. If you need something in that position 12 or 15 or what have you, you're going to have to get it elsewhere. Okay, and that's why we have essential fatty acids that you've got to get those from your diet. Okay, those are your essential fatty acids where they have already had the double bonds added in those positions. Now, if you just need a 3, 6, 9 or something like that, then that's fine. We can do that, but we can't do it beyond position 9. And when I say position 9, it's between 9 and 10 and not 8 and 9. Okay. If you were going to name an enzyme that desaturated fatty acids, what would you name it? A what? What did you say? What?
I said desaturated, but I know it's not
Off of. Oh, whoops, that went too far. It's desaturase. Bada bing! I know, that's why I was waiting to say. Yes, it is the desaturase. Fatty acyl CoA desaturase means it's generic, it's promiscuous in that sense. It doesn't, it doesn't require, it has to be at least only 16 or whatever. What have you, but that is the enzyme that does it. So I was wanting you to say it with conviction. But yes, it is desaturase. That one's a pretty easy one. Like if I asked you, what is the function of this enzyme, I would expect you to say it desaturates a fatty acid. It does require coenzyme A, obviously, attached to it. It goes from a saturated fat to a monounsaturated fat. If you notice, it's this big like a chain reaction. It's not a chain reaction in the sense of free radicals like that, but it's a what is the one I'm looking for? I can't think of the word I'm looking for. There are simultaneous reactions that are occurring, that have to occur in this for this enzyme to work. And so the way that this works is fatty acyl CoA desaturase. Technically, it's called a mixed function oxidase. Mixed function oxidases have two substrates that simultaneously get oxidized. So what does not happen, or what would be an oversimplification, is if we just showed NADPH becoming NADP and this occurring. Okay. So the way that this happens is we go from a saturated fat to a monounsaturated fat using cytochromes. This is cytochrome B5, but yes, so iron 2 plus becomes iron 3 plus, so it gets oxidized. So therefore this is going to be reduced. Okay, or well, it gets oxidized, so it has to be reduced which will oxidize this, which this is going to then be reduced, which oxidizes the NADPH. So it's a chain reaction in that sense, but not a chain reaction meaning free radical, the kind of chain reaction that you're used to seeing, like Cl dots going and making alkyl free radicals and all that kind of stuff. I don't want you to think that's what's happening. But so that technically would be a different class of enzymes called mixed function oxidases. So that means that multiple things, at least two things, are going to be oxidized simultaneously in order for the enzyme to work. But yeah, they're two different substrates. It's not two different types of substrates. All right. So now we have the synthesis of our other fatty acids. So remember, this is the nomenclature from last semester that we talked about. To go from palmitate, and I would never ask you to memorize. Palmitate is probably the only one that you need to memorize, just because we call it palmitate in 16:0. So other than that, I would expect you to know that arachidonic acid is a PUFA, but I don't need you to know that it's between 5, 8, 11, 14. However, if I gave you that 20:4 parentheses, delta, all those, you should be able to draw it. Okay, that's from last semester. We've also reviewed it already this semester as well. So, but yeah, so we go from palmitate to palmitoleic. That's just using desaturates, okay? Because see, it's at position 9, so we can do that. That's fine. We can elongate it there in the ER. Go from 16 to 18 at stearic acid. Okay, you can elongate it to make it even longer, as long as it's saturated. Okay, we can do the desaturation because that's at position 9 to make oleic acid. We cannot go from this to here to linoleic acid. Right? So why? What's the problem? Why can we not do this? It's past carbon number 10. Between 9 and 10, this is between 12 and 13. And so linoleic and linolenic acid, you've got to get from plant diets. Okay. Plant, not planet. I think that's a planet. Plant. Don't go out there and try to be a brainiac. Some great reference there. So, okay. But yeah, that's why those are essential fatty acids. Now, if you notice, we can then go on and go from linoleic to linolenic. Here, if it's gamma 1, because it's at position 6, then you can go ahead and elongate it. So that's how we make arachidonic acid, is you get the linoleic acid from the plant, and then we can go ahead and make it, because you're just either elongating it or you're doing a desaturation prior to position 9. Okay, so that's why that's not a big deal. However, in order for us to get some of the other PUFAs, you have to get alpha-linolenic acid, because we can't do this one. It's got one at 15 as well. So those are the two that you've got to get from your diet. Once again, I don't expect you to memorize their names, except for probably palmitate, because palmitate's the special one. That's the one that fatty acid synthase gets stuck at making. So it's got 16. And then just to recognize, because we talk about arachidonic acid later on, arachidonate later on, to recognize that it's a PUFA. It's big, it's huge. Remember, it's used to make eicosanoids, the thromboxanes and prostaglandins and things like that. Okay. Any questions over this or the logic behind it? Okay. So just to reiterate, they're the essential fatty acids. We mammals cannot make it. The reason why they're important is because eicosanoids come from arachidonic acid. Right? Those are prostaglandins and thromboxanes. And it's indication you spelling. And I'll make this one available soon. Just send me an email. I'll make this PowerPoint available on my site. Okay. Any questions so far? Oh, we're doing well.
How's trans confirmation again?
How do you know if it's cis or trans?
Yeah.
Meaning,
Like if the one is cis or trans.
are these cis or trans?
I can't remember.
Do you want to remember?
Cis.
All natural occurring ones that are free are cis.
Okay.
that are natural. The only trans ones that we would naturally make don't lead to enzymes. It's just an intermediate during the metabolic process. So that's why when you see that partially dehydrogenated margarine or whatever, those are not natural. Those are synthetically made. Okay. Oh, sorry. So this is just to review a little bit. I mentioned this once before, but oxidases versus an oxygenase. So oxidases are it's just a generic name. All of them will fall under those oxidoreductases big umbrella term, but these are like subclasses. So an oxidase, technically speaking, it does utilize oxygen, O2. Remember that's the elemental form for oxygen naturally occurring, it's diatomic. But the oxygen is not incorporated into the product. Okay. That's why we had cytochrome C oxidase from the from the electron transport chain. Remember cytochrome C oxidase? It took oxygen, O2, but it made it to water. It didn't add the oxygen onto complex 4. It made it to water. I do want to point out there are exceptions. Unfortunately, it's like the English language. There are some exceptions, but that if you just had to guess, I shouldn't say guess. If you just had to make a good hypothesis. So that's an oxidase. Oxidoreductase is just a generic term meaning it does a redox reaction typically. Dehydrogenases, we already know that means it uses like NAD, NADH, FAD, FADH2, or their derivatives. Okay. Then we have oxygenases, which I mentioned this like once, I think, so far. But we're going to see more examples of them throughout the rest of the semester. Not this month, because the semester's almost over. This also utilizes oxygen, but the oxygen actually gets added into the product. So this is the way that we have to make a hydroxyl or some type of like ketone or aldehyde. Okay, this is one way that we have to do that. And I think this was the example, if I remember right, from just a chapter or two ago, which was Cytochrome P-450, and it takes an alkane, it turns it into an alcohol. No, lie. It says more about that later. I know that I mentioned this one point in time, but I get confused between my various classes. So, but Cytochrome P-450 takes an alkane and turns it into an alcohol, which is something that we can't do very well in vitro, in organic chemistry. At least if I was teaching it, I would have been marking off, if you just all of a sudden took this alkane and voila, it became an alcohol. You had to activate it somehow, whatever. Our body actually does this with Cytochrome P-450. And then do you remember there are two classes of the oxygenases? What are they? Dioxygenases and mono. Remember this is just O2. So you either put one oxygen in, or you put two oxygens in. And so those are the monooxygenases and dioxygenases. The historical term for the monooxygenases used to be called the hydroxylase because it adds an alcohol group. Because it's adding in one. Usually, dioxygenases you're adding in two. Maybe it's an ester, maybe it's diols or something like that. But you're adding both of the oxygens. Okay, so this is just an example. At this point in time, I would just expect you to recognize the enzyme names or functionalities. Like if I gave you this and covered it up, it's like what class of enzymes is this? You look, okay, it's taking oxygen. We are definitely oxidizing. And now we're adding both oxygens in. So it makes sense. It's a dioxygenase. It makes sense. So this one's technically tryptophan 2,2 dioxygenase. So here's that P450 that I was talking about. I thought we'd already discussed. But Cytochrome P450 is actually kind of a misnomer or misnamed in the sense that it's technically like a superfamily.
Is that the one with the apoptosis?
Some of, and I may have mentioned it. Yeah, so some of them are involved. I mean, they're involved in lots of things. And there's not just one, there are hundreds of them that fall into the superfamily. this cult. No, it's not a cult. But I was trying to think of a faith integration. I couldn't think of one. And so it takes NADPH and as we can see, we're oxidizing it. And then what happens is it goes from an oxidized P-450, it's an iron sulfur protein, to reduced. Then for it to be oxidized, it was going to reduce the actual cytochrome itself. And then what happens there is that this one then goes from oxidized to be reduced to be reoxidized for the enzyme. And it takes that alkane and it forces the oxygen in to make an alcohol. And so that's how we can actually go from an alkane to an alcohol in vivo. Okay, or one way that we have. So you can see, oh look, this is technically going to be a mixed function oxidase as well because we're oxidizing more than one thing simultaneously. Mm-hmm. And then just as this should be hopefully a review from anatomy. Don't know. That or it may have been a while since you've taken anatomy and physiology, so you may have forgotten. But we have eicosanoids. These are types of signaling molecules. They are part of like the paracrine system in the sense that they only happen in a local environment. Okay, so it's not like a hormone in the sense that what's the one I'm looking for? So autocrine, paracrine, and exocrine. Right, that's it. Okay, where it goes long distances. Okay. So these are the eicosanoids. Like I said, I'll put the definitions up on my fire. In fact, I may be able to do it during lab. Okay, so I always do that talking about this because they're in the news all the time. In fact, I just started a new one myself. My doctor just last week put me on a different one. So these are COX enzymes, they're called cyclooxygenase enzymes, or COX enzymes. It's also called H2 synthase. But if you notice, this is arachidonic acid. At this point in time, you wouldn't have to draw from the arachidonic part, but from the numbering part, obviously to be able to draw it. Cyclooxygenase then in turn transforms it. Then we have a peroxidase that ultimately will go on to make it into whatever type of the thromboxane that you need or prostaglandin that you need. But I wanted to point this out. These COX inhibitors, for example, aspirin is a COX inhibitor. They inhibit cyclooxygenase. To me, this kind of looks like a fish. I don't know why. See little eyes. But go beside the point. But and so, but the COX inhibitors actually inhibit this. We actually have two forms of COX enzymes. There's COX-1 and COX-2 in mammals. Okay, COX-1 is what's going to make the prostaglandins for your stomach. COX-2 make the prostaglandins that are associated with like headaches, for example, pain, with your fever, with inflammation. Those are the ones that usually are the ones that when people are having problems with the prostaglandins that they're having problems with. The issue that we have is with some of these inhibitors, they would have these broad-based COX inhibitors where it inhibits both COX-1 and COX-2. So for example, something that's too broad-based, then it can cause stomach problems because of the fact that it's inhibiting COX-1 and not just the one that's causing the headache or the inflammation or what have you. Okay, so those are broad-based. So COX-2 inhibitors that we have, of course, these are the NSAIDs. And I have a better picture that I actually showed this last time in enzymology, but there's a serine. This is, by the way, is not the active functional group for the enzyme, but it's in the binding site, and so it blocks. So when aspirin binds, it's a suicide inhibitor. You can't really see it right now. It's a suicide inhibitor. It binds, it actually acylates, and it's irreversible. Okay, so now this acetyl group blocks the arachidonic acid from coming into the active site. It can't fit anymore. Okay, and you get salicylate. Salicylate's also an anti-inflammatory. It's just not as potent. Okay. Same thing with methyl salicylate, wintergreen oil. Whereas some of these others, like ibuprofen and naproxen, they are not suicide inhibitors. Okay, the NSAID stands for non-steroidal anti-inflammatory drugs. Okay. Oh, whoops! I did not mean to do that. That should be there. The problem was, a lot of these, as I mentioned, also inhibited COX-1, so then it caused a lot of side effects. So then they started to try to make COX-2 specific inhibitors. It only inhibits, the COX-2, you don't have any stomach problems. They thought that this was amazing, okay, in the 1990s and early 2000s. Okay, they made covers all over. They said, look, now you don't have to have all the worries and all the problems from like taking aspirin or acetaminophen or some of those. And so we have Vioxx, Bextra, and Celebrex. And so, however, a lot of these have since been pulled off the market because they have dangerous side effects. They were rushed through, they had dangerous side effects, and but actually I just started taking Celebrex recently. And so for inflammation, so it's still around. Some of these others have been pulled away. I think some of them could cause cardiac arrest. Some of them, have some really weird things. Okay. Are there any questions just in general about this? So this section is really, really tiny. Awesome.